Dear learners, greetings from IIT Guwahati. We are in the course Fundamentals of Compressible Flow, Module 8, that is Measurement, Diagnostics and Experimental Facilities for Compressible Flow. So, in the first two lectures, we covered some of the classical measurement techniques such as pressure, temperature, velocity, and also we covered some basic aspects of advanced measurement techniques involving Schleeren apparatus, Shadowgraph techniques and interferometer. Having said this, we are now going to start some of the aerodynamic facilities which are governed through compressible flow. So, the first basic facility that we have is that a subsonic wind tunnel, and in this lecture we will discuss about some basic philosophy of the subsonic wind tunnel, where we are looking at the flow Mach number which is mostly subsonic, and at the same time we will also look at some of the situations even in a subsonic flow, if at all the compressible effect is not taken into account, then we can treat this flow phenomena to be incompressible. So, in some sense that the subsonic wind tunnel uses gas which can be treated as a compressible flow, or it can be also be treated as incompressible flow depending on the wind speed at which the experiments are conducted. Now, when we are talking about wind tunnels, just like taking experiments will have a meaningless unless and until you involve some measurement, diagnostics or philosophy. So, the total summary of this particular lecture is that we will discuss about some of the basic aspects of wind tunnel and its component, its working principle, and subsequently it will be followed with the wind tunnel instrumentations just to measure pressure, velocity, the forces and flow visualizations. And towards the last part we will try to see that if you have a subsonic wind tunnel, how you are going to evaluate its performance. By evaluation of performance, I mean that we need to calibrate it, so that we can say that wind tunnel is ready for experiments. Now, once it is ready for experiments, then I will give a brief overview what type of research that can be performed in a subsonic wind tunnel. So, this is the brief summaries of this lecture. Now, we will start with the fact that let us discuss about something on aero test facility. In aerodynamic sense, the test facilities involves different flow regime. So, we all know that compressible effect of a moving gas becomes significant when the Mach number is greater than 0.3, and if it is less than 0.3, it will be incompressible. In fact, when you are dealing with this flow in a wind tunnel which is subsonic, either it will be close to incompressible limit or it can be low subsonic flow, and that is what the Mach number decides whether it is a flow is a subsonic or not. Then we have a transonic tunnel for which Mach number is in between 0.8 to 1.2. We have supersonic tunnel, we have supersonic flow for which Mach number is more than 1.2. We have hypersonic flow, Mach number is becomes more than 5. Now, when Mach number becomes more than 5, then after that if you want to analyze the flow field, such flow fields we call this as a hypervelocity flow. Hypervelocity flow has a very specific characteristics that they have when such flows are encountered during re-entry speeds in which the gas is brought to rest, and as a result the pressure and temperature gets suddenly very high and dissociation effects become significant. So, if you look at this particular equations, the Mach number is a function of velocity and speed of sound, but again the speed of sound is a function of square root of gamma r t. So, what happens really in a hypervelocity situations, that the temperature is so high that it is going to alter the values of gamma and r. So, as a result the speed of sound is also going to change, and these dynamic effects always says that nowhere we can say we can have a Mach number, a consistent Mach number. So, such flows are characterized as hypervelocity flow, and those velocities are considered as suborbital velocity, for which speed is less than 8 kilometers per second, superorbital velocity for which speed is higher than 8 kilometer per second, and escape velocity with respect to earth is about 11.2 kilometer per second. So, anyway this is the towards the high end, but what we are going to look at a very low subsonic flow situations where we are going to consider a test facility. Now, after having this compressible flow regime, the wind tunnels are classified as subsonic wind tunnel, transonic wind tunnel, supersonic wind tunnel and hypersonic wind tunnel. Now, apart from these classifications, based on the geometric arrangements, so the wind tunnel can be open circuit type and closed circuit type, and based on the flow operations it can be suction type or blow down type. Based on the suction flow means there will be a fan which sucks the air from one end, and blow down type means we have a blower that allows pushes the air from one end. Now, based on the application requirement, we have V/S TOL tunnel, that is vertical short takeoff and landing aircraft. That means these are aircraft specific tunnel for which the tunnel is configured. We have free flight tunnels, we have spin tunnels or vertical wind tunnel, propulsion tunnel, icing tunnel. So, these are the very specific requirement for which the wind tunnels are designed. But however, we will talk about only a very generic subsonic wind tunnel, and that too low speed. So, we will consider a subsonic wind tunnel, which is a very basics and preliminary tunnel for aerodynamic testings. So, basically this wind tunnel consists of 5 major segments. One is drive section, settling chamber, contraction cone, test section and diffuser. So, the drive section essentially provides the necessary pressure difference, so that we get a desired velocity in the test sections. So, the drive section normally has axial fans, and to drive these fans we have motor arrangements. So, the drive sections mainly consist of fan motor assembly. Now, once the fan drives the flow, it enters the air enters into the tunnel, and this in a sense that when you actually do the aerodynamic testings, we need a streamline flow patterns, and it is a axial flow or straight path has to be followed, and also we have to minimize the turbulent intensity. To do such activities, what we have to do is that we need a settling chamber that comprises of honeycombs and screens that serves the purpose of smooth flow streamline pattern in the test sections. Side by side, it also reduces the free stream turbulence and mean velocity non-uniformity. Then the air enters to a contraction zone where the speed is increased. So, this is simply Bernoulli's equation principle. So, when a subsonic flow enters a converging passage, its speed increases. Now, depending on the shape and size of this or geometry of this contraction cone, the desired speed is achieved in the test sections, and where the model testings or experiments are carried out. Now, once the experiment is over, the air has to be smoothly guided out of the tunnel. So, all of a sudden if you allow the air to go out, we will have a huge pressure loss or huge energy loss. To avoid such things, we have a diffuser, and it is nothing but a device that lowers the speed of the air, and consequently air is released to atmosphere with minimal loss of energy. So, this is the two variants of a subsonic wind tunnel. One is open circuit wind tunnel, other is the closed circuit wind tunnel. So, in open circuit wind tunnel, as I said, that we have a drive sections where fan or motor arrangements are kept in one end. So, once it fan or once the fan is driven, air sucked in from the other end, and when air passes, it enters through first settling chamber, then contraction cone, then test sections, and finally diffuser. So, basically air enters from one end and goes at the other end. So, this is how we go do for a open circuit wind tunnel. Now, in some arrangements where air is not plentifully available, people think of closed circuit wind tunnels, so where same air is circulated within the tunnel. But however, in general sense, the low speed wind tunnels are mostly of open circuit type, because it is a better that we get a fresh air to get circulated, fresh air that enters from one end and goes in the other. And closed circuit wind tunnels are typically avoided because of lot of other complication issues as far as the recirculation is concerned. Now, with respect to analysis of a subsonic wind tunnel, I will try to invite your attentions to a unique facility of wind tunnel and IIT Guwahati in the Department of Mechanical Engineering, which is a low turbulence level wind tunnel, for which turbulent intensity is less than 0.3%, and this facility gives a uniform wind speed of known value, and for which the fluid phenomenon is to be investigated. In fact, it is considered as a state of art facility to carry out various aerodynamic investigations as well as wind energy research. So, we will talk about what type of research in the later part of this lecture, but I will now bring your attentions to the very basic components that are involved in a low speed wind tunnel, and with respect to unique facility at IIT Guwahati, all these explanations are provided. So, this wind tunnel is it is equipped with a classical measurement instruments such as hot wire anemometry, 3D traverse, truck sensors, pressure scanner, advanced instruments such as PIVs and so on. So, if you see this particular, it is about 15-meter long tunnel, and we will go one by one. These are some images that we can see. This particular part, what we can consider is as a settling chamber where the flow enters, and we have this honeycomb and screen structure which is here, and the drive section is somewhere in the behind this. So, you can see this is the drive part which drives the flow from one end, so that air from the other end enters into the tunnel and it enters into the test sections. So, a closer view of the test section looks here, and this test section is instrumented with various data acquisition systems and others. Size of this test section is about 0.6 by 0.6 meter into 2 meter length. So, it is a square cross section of 0.6 meter and its length is 2 meters. And we have a 300 HP motor, AC induction motor that drives the fan, and for which the air gets sucked into the tunnel. So, this is a very schematic view where it represents the entire size of the tunnel. So, this particular and each unit will have its own shape and dimensions. So, first thing we have a drive things, I have already mentioned, it is a 300 HP induction axial flow fan and induction motor driven by 330 HP induction motor with AC supply. Diffuser part is of 4.2 meter length, test section is 2 meter length, the contraction part is 1.8 meter length, and honeycomb plus screen structure will have about 0.9 meter length. And some silent features of this wind tunnel is that when you talk about wind tunnel, first thing we ask what type, how much speed we are going to test it. So, and what is the maximum size of the model which we are going to, what one can use. So, this depends on this test section size. What we have is 0.6 into 0.6 meter and 2 meter long, and wind speed can be up to 50 meter per second. That means, the wind tunnel has a capability to go up to a speed of 50 meter per second. Rest of the things are all given here. We have honeycomb, screens, contraction part, As far as user point of view for aerodynamic testing, these are just a bare minimum information, and now we will go to the different instrumentation part of this wind tunnel. Just like if you have wind tunnel without any instrumentation has no meaning. So, we must build the wind tunnel with necessary instrumentations. So, the bare minimum instrumentation that is required here is pressure measurements we must do, velocity measurements. So, for the pressure measurement we have pressure scanner, pitot probes, and for inclined manometer, U-tube manometers. So, these are these very possible combinations. And for velocity measurements, one way is that we can get the velocity measure from the pressure measurement as well, but a more unique feature or instrument wise you can do a hot wire anemometry study. So, through hot wire anemometry we can measure the velocity, and there is a 3D traverse system. 3D traverse system means since we have a 2 meter long test sections. So, instead of in a sense that if you want to measure at different locations of the in the test sections, then you require some mechanisms that during the tunnel operations we can play with the position of the model within the test sections. So, that is what instead of doing it manually and stopping the wind tunnel. So, we have a 3D traverse systems which can by which we can move the aerodynamic model within the test sections even during wind tunnel running conditions. Now, apart from this we also need a force balance to quantify the aerodynamic forces and other things, and we also require some flow visualization methods. Flow visualization method means many times the fluid flow pattern or flow behavior or streamlines pattern needs to be studied, streamline or streak line patterns needs to be studied. So, for that reason we need a flow visualization techniques. There is another thing, what is a 3D printer. Of course, the 3D printer is not a requirement for this wind tunnel, but it is a requirement for the model fabrication which needs to be tested in the wind tunnel. So, 3D printer means that normally when you do wind turbine research or aerofoil shaft model testing, then 3D printer is the latest version of manufacturing technology through which we can fabricate the blades or aerofoil structures that needs to be tested in the wind tunnel. So, that is what it is, just I have written, it is just a part of this wind tunnel, and this is mainly required for model testings. So, you can say that this 3D printer is mainly used for model preparation or fabrication with advanced technology or advanced method. Okay. Now, we will discuss them one by one. So, first thing we will start with a pressure scanner. So, before you go for this pressure scanner, we must know some of the basics of pitot probe. So, in my last lecture I have elaborated that what a pitot static probe is all about, and it measures the static pressure as well as the dynamic pressure simultaneously through an U-tube manometers. So, this is also similarly useful for wind tunnel situations. So, if you look at this particular figure, so this is a pitot static probe in which we are going to measure the stagnation pressure and static pressure simultaneously. So, we have a static straps which is mounted on the circumference. So, it measures the static pressure given by this particular arrow symbol, and stagnation pressure is measured or total pressure is given by this particular arrow symbol, and dynamic rest of the thing, that is difference between two, is the dynamic pressures, and it happens due to the velocity. So, a brief equations using the total pressure can be divided into dynamic pressure plus static pressures, and that can be related to by Bernoulli's equation related to velocity of the flow, that is u. And knowing the value of manometric fluid density, and in this case mostly it is methyl alcohol, you know this density, we know G, and we also know the elevation difference. So, from this we can actually calculate the velocity of the flow in the tunnel. And these are the some other pictures. If this is the main pictures, and this is how the probe looks like, and these probes has many variants. One can have a pitot probe, a straight type, one can have a curved and bent type, one can have a L bent type, one can have a straight type. So, there are so many variants probe is possible. And apart from this, we also have a pressure scanner. So, pressure scanner means in order to get rid of these measurements manually. So, we have a electronic way of recording the data. So, we will have a system in it is a device that it measures pressures from multiple ports simultaneously. So, you can see this is a 16 pressure tube, and each tube is nothing but a one particular pitot tube. So, this 16 pressure tube they are connected to a single control panel, and the data are collected simultaneously at different locations in the wind tunnel. So, as a result, that means at a given point we will have about 16 pressure data with which we can say this, or you can talk about the accuracy level of the measurements. So, this is what we call as a 16 channel pressure scanner. The next important aspect is the hot wire anemometry. Hot wire anemometry is very classical techniques for measuring the velocity in a wind tunnel environment. So, it is a device to measure the fluid's velocity, or in fact, it is an instantaneous velocity, and it is good for measuring the fluctuation part as well. And when an electrically heated metal conductor is kept in a flowing stream, the heat gets transferred from the wire to the fluid, resulting decrease in the wire temperature, and which further results in the change in the wire resistance. So, this variation in the wire resistance allows us to calculate the flow rate of the flow stream. So, this is how the basic principle is all about. We have a wire, and this wire is connected to a prong, and it is connected this particular prong, and the where two ends of this prong is connected to a Wheatstone-Bridge circuits. So, what we see is the hot wire here, and these are the electronic circuit arrangement based on the Wheatstone-Bridge pattern. So, as a result, we get a change, any change in the resistance, it gets acquired by the change in the voltage. And in fact, the choice of the wire is very vital for selection of this hot wire probe. This probe is very about 3 millimeter long and few micron meter diameter, and this is typically made out of tungsten, platinum iridium alloy, which or platinum rhodium alloy. Why this is required? Because these are very prone to change its resistance when it is heated electrically. Now, ultimately at the end of the day, we are going to measure the velocity of the flow, and from the measured data from the hot wire anemometers. So, the very basic law that governs the hot wire anemometry principle is the King's law. So, what it says is that if E is your measured velocity and it is related to E square is equal to A square A plus B u to the power n, where n is an velocity index and its value is 0.5 for our low speed wind applications. A and B are calibrated compression constant for a particular applications, and these values can be decided from the during calibration experiments. So, what the King's law tells us that if you are able to measure the velocity or value of voltage change from this Wheatstone-Bridge circuit, we can correlate with that with respect to wind speed. So, this is how it happens is that, and this probe can single point probe or dual probe or triple sensor probe. So, that means we can have velocity at a point maybe in 3 directions x, y and z direction, then you can take a average value of that. This is what the theme of the hot wire anemometer probe is all about. So, the relation of determining heat stored in the air is the governing principle, and it is nothing but the difference in the electric power and convective heat transfer out of the air by neglecting the conduction and radiations. Now, for our wind tunnel applications, this particular hot wire anemometry is a very fundamental tool for measuring the velocity, and this probe has a length about 8 to 10 millimeter, and in fact, and it is a tungsten platinum coated material. Probe has wear length of prong length is 8 to 10 millimeter, but the probe wear length is about 3 millimeter, and its probe wear diameter is about 10 microns. So, you can see this kind of miniature version of the probe which are being used to measure the velocity in the wind tunnel. And in fact, it has been shown that we can have a, it is very good to measure the suitable for flow speed between 3 to 30 meter per seconds. And of course, there are other instrumentations that we want to measure output signal as a instantaneous mode or fluctuation mode, and we can have a single wire channel or multiple probe type things. Now, when you get the things get the signal from the probe, we need some kind of filtering. So, it can be low pass filter or high pass filter depending on the flow conditions what we have inside the tunnel. And this probe has also amplification factor starting from 1, 10, 100 and thousands. The next important segment of wind tunnel instrumentation is the 3D traverse systems. So, why we require 3D traverse systems? For example, if you want to conduct a test in the test section of a wind tunnel, we require the movement of the probe, maybe let us say hot wire anemometer probe that has to be mounted, and it has to move during the tunnel running conditions. So, to do that we require a 3D traverse systems in which probe is mounted, and this 3D traverse moves in x, y and z directions. So, it has a range of 600 millimeters, diameter and pitch of the screw is 15 to 15 mm and 5 mm, and it is equipped with a stepper motor controller. So, by controlling this motor we can move this traverse, and so this particular unit also is based on microcontroller based programmable unit. Okay. So, next important aspect is this 6 component force balance. So, if you look at the aerodynamic theory, normally a aerodynamic body encounters during its motion when it is traveling, there are 3 forces and there are 3 moments that comes in. What are the forces? The drag which comes in the direction of the wind speed, and the lift which is perpendicular to the drag, and there is a side force which is nothing but the perpendicular to the lift and drag force. So, basically lift, drag and side force are mutually perpendicular to each other. Now, for each force we can have a moment. So, we can have a weighing moment, we can have a pitching moment and we can have a rolling moment. So, 6 component force balance is all about is that it is a single unit which can measures all the three forces as well as 3 moments simultaneously on a given model and at given wind speed. Then we can say that we will be able to measure the aerodynamic forces on the body. So, and this particular force balance is consist of a strain gauge type balance, and this has a capability of measuring lift, drag and side forces given by these numbers. Lift, maximum lift it can go up to 10 kg, drag it can go up to 3 kg, side force it can go for 3 kg, 2 kg, and pitching moment, rolling moment, weighing moment are 50 kg, 30 kg and 30 kg centimeter respectively. The next segment of the instrumentation is smoke and laser sheet visualizations. So, while talking about flow visualization in a classical fluid mechanics term, we might have known about the streak lines, path lines, okay, and these and streamlines anyway is the theoretical lines in which the when a tangent is drawn, it is always, when a tangent is done, it gives the direction of the flow velocity. But in reality, in experimental sense, we need some kind of lines, either path line or streak line, to study the direction of the wind speed or wind velocity in the tunnel. To give a visual pattern, we need to illuminate the tunnel of in which air is moving. So, a classical way of doing this is a smoke based or through generating smoke, and propagation of smoke will give the desired path of followed by the wind or air. So, this smoke or laser sheet are two approaches of flow visualization that are used for wind tunnel experimental study, and in smoke visualization the smoke is generated through burning of some incandescent fuel or through electrical heating, and this smoke generation through the electrical heating is carried out by a nichrome wire upon which a paraffin oil is poured vertically in a regulated fashion. So, the flow of the smoke path allows to study the streamwise direction of wind speed, and laser sheet is an additional attachment of flow visualization that is mostly used in case there is a low visibility and the field of interest is towards the particular plane. Okay. So, these two things run in parallel. If you are unable to see the reality in the there is a low visibility, then we can illuminate this test section through a laser sheet. And in our wind tunnel, we have these capabilities of these smoke and laser sheet flow visualization techniques. Then we will move to last part of instrumentation is the 3D printer. So, as I mentioned that 3D printer is not an integral part of the wind tunnel, but it is a very good tools or small scale or small size instruments in which we can fabricate various aerodynamic models, aerofoil shape models for study in the wind tunnel. So, it is nothing but a concept based on additive manufacturing, that is the construction of 3-dimensional object from a CAD model or a digital 3D model. It refers to the variety of processes in which the material is deposited, joined or solidified through under the computer controlled situations of 3D objects. And in our facility of wind tunnel laboratory, we have a 3D printer which is a fuse type deposition modeling or FDM type. This printer supports several materials, and in particular polylactic acid materials, PLA materials or polymer type materials, and in fact these are low weight materials, and this gives a benefit of low weight, but high strength materials, and also they are biodegradable and eco friendly in nature. So, this 3D printer requires a nozzle temperature of 210 to 35 degrees centigrade, where bed temperature is about 60 to 70 degrees centigrade, and this turbine design for wind turbine blade design, the printing feels the density of 60 to 70% is good enough for the structural stability for the turbine to be tested at 3200 rpm. But anyway, that is a different thing, but what the basic things that I need to say is that we have a 3D printer, and this is the printing process, how we can pour the materials and how we can how the printing process can happen, and this is the nozzle shape that is that actually pours the material or makes the shape of the object. And based on this, we can see there are some kind of blades, this aerofoil type of blades. This is another that hub, wind turbine hub which is being fabricated. This is another type of aerofoil shape model, and this is a camber type of aerofoil, and these are the wind turbine blades. So, what I can say is that a simple small laboratory type handy tool, 3D printer tool, it is possible to fabricate so many aerodynamic models in the laboratory at a reasonable cost. So, that is the advantage that this 3D printer used for our applications. And once we have every instrumentation is ready, then we can say that what about your tunnel characterizations. So, to characterize the tunnel, we want to say that for example, a particular application require wind velocity of 10 meter per second. So, how we can say precisely that 10 meter per second is coming or not. To do that, the tunnel need to be calibrated. Now, in another situation that we require a velocity of 15 meter per second. So, what you need to do again in a calibrated tunnel, so that we will get 15 meter per second. All sorts of things has to be addressed, and we call them as wind tunnel performance and its characterization. That means, the wind tunnel is unique in nature, and this gives this has to cater or solve the need of the requirement. So, before performing the experiments, the wind tunnel needs to be calibrated adequately for wide range of velocity. So, the calibration of the tunnel could be carried out by evaluating the relation between the revolution of axial fan. That means, because the wind speed comes because the fan is rotating. Now, when the fan is rotating, we must regulate the RPM of the fan. So, the RPM of the fan must be correlated with the wind speed, and when we say wind speed, that wind speed in the test section must be measured. So, all these three things to be linked together, and this measurement, when you do measurement, is normally done at different locations of the tunnel, and mainly and most of them is done at the wind tunnel test sections, and in some case we also need to require the entry at the entry point. So, there and for the requirement a different demand or requirement or situations, we can use the different methodology like inclined tube manometer or pressure static probe. So, you see here that when a pitot, this is a pitot static probe that measures the pitot pressures as well as the static pressures, and difference gives you the velocity. And in another application, we have an inclined tube manometer is useful to measure the velocity in the test section of the tunnel. It is used to measure the velocity in the tunnel test section inlet, whereas we can use the pitot static probe at any location in the wind tunnel. Now, moving further, for wind tunnel study, it is expected that velocity of the flow should not be is more than 3 meter per second. So, at that point of situation, the inclined manometer is a better approach than U-tube manometer. And why it is inclined method is better? Because it is a curved tube with manometric fluid inside, and the prime benefit is that for a small or low amount of pressure, the manometer will produce large liquid movement relative to the tube's graduations. So, as a result, your accuracy level will go high. And another factor that drops in is the sensitivity of manometer tool. And when you talk about sensitive, inclined manometer is a better approach from this U-tube type, because it gives a accurate pressure level. And here what you can see is a U-tube manometer which measures the velocity at the inlet of the test sections. So, you can see we have the schematic view, we can say the inflow that wind enters through the test section, and this particular point is the location at which the U-tube manometer is mounted, and the pressure which is one point of time, which is just when it enters to the contraction zone, the total pressure is measured and fed to here, and at this particular point another value of pressure is measured, which is nothing but the static pressure, and this static pressure and total pressure difference gives the velocity of the wind speed and at the time of inlet. So, here what we can see is that we have two parameters, one is the density of manometric fluid rho m and density of air, and these two densities are known to us, and manometric fluid is typically methyl alcohol and for which the density is normally known and density of air is 1.2. So, based on these relations we can have a number 3.58 square root of delta h, and delta h is in millimeters, and this is nothing but the difference in the elevation. Okay. And once we have this, once we measure the wind speed, at the same time we have to know that maybe that for a different and this is particular curve talks about a calibration curve of the wind tunnel. What it means is that a different if I want a wind speed about 30 meter per second, then what should be my fan RPM. So, you can drop something that fan from this calibration curve we can find out that fan RPM should be 800. Now, when I say fan RPM is 800, then I can exactly say that we will actually getting the 27 meter per second, although it is designed for okay. So, fan RPM is 800 means it will give the 27 meter per second. So, this means that by regulating if you want a desired wind speed, we can adequately control the RPM of the fan, by which we can regulate this thing, and this has to be done during the calibration itself, and we do not require to do subsequent calibrations when we are actually doing the model testings. So, at that point of time for 27 meter per second we must run the fan as 800 RPM. Once you say that, then you can accurately say that wind speed about 27 meter per second. So, this is the what we call the calibration and characterization of the tunnel. And there are some other kind of studies that we also need to perform to have a precise calculations, that most of our research requirement it needs that we have a precise data as far as the accuracy is concerned. So, when you have a speed less than 10 meter per seconds and the tunnel characterization needs to be evaluated at such low speed conditions, then we must do some kind of data driven philosophies, and based on the characterizing the slope of the calibration curve, and we call them as a probe sensitivity. So, that means if you have a wind tunnel RPM and if you have a precise velocity, so we can plot the curve and try to see that what is the sensitivity. Sensitivity can be calculated, I mean how much for a 1 RPM inaccuracy will lead to how much change in the wind speed. And of course, there is other method by calculating the standard deviations. So, this is actually required when you need a precise data. The next important factor that we must say that, and in fact most of application require what is the turbulence level in a wind tunnel. So, to study this, then we must say that our wind tunnel is good, that means is a low turbulence intensity tunnel, which means that the turbulent intensity is less than, could be less than 0.3%. Now, how do we make this turbulent intensity less than 0.3%? To do that, we require a precise calibrations to get the data, that is instantaneous velocity. So, what we have seen in Pitot probe is this, that is just average velocity, and here what we have to require, you have to take the velocity with respect to time, and on top of that when you take a particular signal, that means you have to take the velocity in the form of a signal. So, this particular plot shows the velocity plot in the test section of a tunnel, and this value is about 3.25 meter per second, which is the average, if you say average wind speed, but there are fluctuating components u, and this average v is u bar, and this data is taken for about 1 second. Now, if you want to quantify what is the intensity, what is the level of intensity or fluctuations that is coming out in the wind speed. So, you know how to quantify this. So, for that we have a hot wire anemometer which gives two velocity components. One is the average values of velocity, average value of voltage which corresponds to average velocity, other is the fluctuation component u that gives the fluctuation in the velocity. So, both can be correlated, and a factor that defines is the turbulent intensity, which is nothing but RMS value of u divided by u. U is your free stream is the total velocity. So, based on this and the u RMS value can be calculated as 1 by t integral of u square dt 0 to t square root of entire square root or to the power 0.5. So, this particular data will talk about the calculation of turbulent intensity. So, basically hot wire anemometer involving King's law will give you the average component as well as fluctuating components, that is in terms of signal. By post processing the signal we can calculate the u RMS value, and from this we also have average value, and from this we can calculate the turbulent intensity. And this particular plot talks about the for a wind tunnel which is being calibrated in a variety of methods. The first plot talks about tunnel RPM versus u, which we have already shown. Through hot wire calibration we can talk about E, this voltage divided versus u, and we can talk about E square versus square root of u, and also we can have y by h divided by sigma by u. So, all these plots talks about the characterization nature of a wind tunnel. So, what the very basic fact is that we need in all the cases we need a factor which is normally called as R factor or R square, and for this if it is a very low intensity low turbulent intensity tunnel, this R square should be in the order of square root its value should be 0.999. That means that way that we can say we have characterized the wind tunnel for a very low turbulent intensity value less than 0.3. And this is the another part where we talk about the sensitivity of probe, and the sensitivity of the hot wire probe is nothing but it is the ratio of change in the probe voltage with the change in the fluid velocities. So, another kinds of plots that can be plotted here, and this unique plots will talk about, or we can say we will talk about the characterization part of the wind tunnel. So, the more and more analysis you do, that means the more and more precise information that we are going to get out of the tunnel. So, this is all about the wind tunnel and its instrumentations, but however, there are many research opportunities that is possible from a subsonic wind tunnel. In the current philosophy of streams, like in a interdisciplinary concept or approach involving mechanical, aerospace, energy, instrumentations, and if you merge all these areas together, there can be many research problems which can be studied in a subsonic wind tunnel. So, first category of the problem is classical fluid mechanics problems, where you talk about flow over flat plates, aerofoils, flow over cylinders, and boundary layer study, suction, blowing and transitions. Of course, those classical problems are obsolete now, and people are moving to advanced problems. One such advanced problem is to study the cooling mechanism in gas turbine blades. This is another new area. Wind tunnel can be an effective tool to give the different wind velocity, and mainly we can talk about here we can talk about when you talk about gas turbine engines, the flow velocity could be as high as a higher subsonic range. So, apart from this aerospace community and aerodynamic study, wind tunnel also gives a good amount of opportunities to study wind energy research and wind farm modeling. So, there are lot of important aspects that can be studied, that is cascading effect of wind turbine blades, characterizing the transitional behavior of wind turbine wakes. Normally, if you have a cascading tunnel, multiple wind turbines are arranged sequentially, and each wind turbine blades will have a significant effect on the subsequent turbine. So, in a sense that characterizing the transitional behavior of of this wind turbine wakes gives a new area in which we can actually say that what is the effect of one wind turbine rake with respect to other. Now, apart from that, we can have aerodynamic studies of wind turbine blades for harnessing offshore wind power. We can think about many kind of innovative blade designs for wind turbine blades. So, through the 3D printing technology, And of course, we can think of biocomposites, like nowadays we have biocomposites or wind turbines blades that are fabricated from high quality bamboos. So, those can be useful blade materials or tools that can be studied, and what is their main intention of their application is for localized rural power generations. And many people also do study that for a augmentation techniques. There are many augmentation techniques. So, in the existing wind turbine blades, many augmentation techniques can be applied just to study that how the performance in terms of power coefficients, how they are torque, that can be improved. Now, apart from that, we have horizontal axis wind turbine, vertical axis wind turbines, those things can be studied, and those wind turbines with different types of blade materials is the another kind of challenge that can be looked into by through this wind tunnel research. And recently, with respect to aerodynamic community, if you talk about micro air vehicles, normally those vehicles require a design of flaps, like flapping of birds, how the birds fly. So, such a small bird is a very small insect, and if it can fly, then in a sense can we fabricate a vehicle which can fly or through and so that we can have a flap mechanism, and if you want to have a micro air vehicles, and this is mainly used for surveillance purposes, and it can be used for variety security applications, and such kind of studies also can be performed in the subsonic wind tunnel. So, with these research concepts, I will conclude this lecture for today. Thank you for the attention.